Hello and welcome to tutorial number 1. Our topic today is units and measurements. Before we get started with that, a quick reminder that the notes to accompany each and every one of these tutorials is available online through my website, and I do highly recommend that you have those in front of you as you're going through these tutorial videos. So you'll find that the first slide of those notes will just have a list of the goals for that particular tutorial, and then starting on slide 2, you'll see that everything really correlates well to what I'm going to be presenting up here on the board. So very much to your advantage to have that in front of you as you're watching these videos. With that said, let's go ahead and get started. So I like to start out this topic by just mentioning that it's really not a new topic for any of you. You make measurements all the time, and you report those measurements with units. Every single day we do this. Simply driving our cars. We monitor our speed in miles per hour so that we don't get a speeding ticket. So we are making a measurement and we are using a unit. Miles per hour would be our unit. Anytime you followed a recipe in the kitchen, you're making measurements and using units. Cups, tablespoons, teaspoons. If you're really into cooking and baking, you might even measure things out by their weight in grams or ounces. So not a new topic for anybody out there. You've done this before. But what might be new to you are the type of units that we use in a science class. In science, we use the metric system. And this is all on slide 2. So we're starting off with slide 2 here, the metric system. Which is based on the decimal system. And in the metric system, there are different base units depending on what it is that you are measuring. So if you're measuring mass, then the base unit would be the gram. Let's write here base units. Okay. And the abbreviation for gram is a lowercase g. If you are measuring length, the base unit is the meter, abbreviated with a lowercase m. If you are measuring time, the base unit is the second, abbreviated with a lowercase s. And if you are measuring volume, your base unit is the liter, and that's abbreviated with a capital L. So very important there. The others are all lowercase. The liter is a capital L. All right. And then to these different base units, we would add different prefixes, and those different prefixes represent different factors of 10. So that's why we say it's based on the decimal system. So let's write here, we are going to add prefixes, which represent different factors of 10. Okay, so I'm going to introduce just 7 prefixes in this tutorial. If you're taking a chemistry class, you'll want to pay close attention to which prefixes your instructor wants you to know from the metric system. It could be more than I'm introducing here, maybe it's fewer, so just pay attention to that. Okay, so let's erase here. Okay, so those 7 metric prefixes. I'm going to write down the prefixes here. So we've got kilo, hecto, deca. It's kind of messy there. Make that a better D. Deca. I'm going to put a line here because everything that appears above the line represents a factor of 10 that is greater than 1, and then all the prefixes that I write below the line are going to represent factors of 10 that are less than 1. So deci, centi, milli, and micro all go below the line there. Okay, so kilo means 1,000. Its numerical value is 1,000. I'm going to also write that in scientific notation. If you're not familiar with scientific notation, don't worry about it. Just tune into tutorial number 2, because that's when we'll be covering scientific notation in detail. So I'll go ahead and write 10 to the 3rd power here for 1,000 in scientific notation. And then the abbreviation for kilo is just a lowercase k. So if you were trying to write the abbreviation for kilogram, it would be a lowercase k, and then the abbreviation for gram, which is a lowercase g. So it would look like that. All right, hecto is 100, or 10 to the 2. Abbreviation is a lowercase h. Deca is 10, so 10 to the 1st power there. And the abbreviation for deca is DA, so as not to confuse it with deci, which is just a lowercase d. So very important that you know that deca is lowercase d, lowercase a. Deci is a 10th, so 0.1. And again, the abbreviation is just a lowercase d for deci. Centi is 100th, 0.01. Let's go ahead and still write these in scientific notation here. So 10 to the negative 2. So centi's abbreviation is just a lowercase c. Milli is 1,000th, so 0.001. 10 to the negative 3, and the abbreviation for milli is a lowercase m, and then we have micro, which is a millionth, so 0.000001, or 10 to the negative 6, and the abbreviation for micro is a symbol called mu, and it just looks like a cursive lowercase u. It's called mu. All right, so those are our 7 metric prefixes. Again, your instructor may want you to know more, they may want you to know fewer, so pay close attention to that in class. All right, so I'm going to erase here. So I like to go ahead and do a little visual for the metric system at this point. I think it's very helpful. I'm a very visual learner, so a lot of my teaching is very visual as well. So let's pretend that I took a meter stick and very carefully measured off the length of just 1 meter, okay? And then if I very carefully, let's do it even in a different color, let's go to the blue pen, measured off 1/10 of that meter. Okay. Well, 1/10 of a meter, we could also represent that length by using the appropriate prefix from the metric system. Deci is 1/10. So we could instead call that length 1 decimeter. D, lowercase m. Okay. Let's go to the green color now. Let's say that I carefully measured off 1/100th of that meter. Okay, again, we could use the metric prefix. In this case, the appropriate metric prefix for 100th would be centi. So that length could also be called 1 centimeter. Okay. Let's go to the red pen and let's carefully measure off 1,000th of a meter. Once again, we could also use the appropriate metric prefix for 1,000th. That would be milli. So we could call that length 1 millimeter. Okay. Okay, let's go the opposite way. Let's say that I had 10 meters. Once again, we could use the appropriate metric prefix. Deca is 10, so 10 meters could also be called 1 deca meter. And remember that deca, so as not to be confused with deci, is abbreviated DA. So we get 1 DAM for 1 decameter. Okay, so I won't go on and do hecto and kilo. I think that's probably enough examples there. So let's move on. Okay, so you're probably starting to see that we have an awful lot of units to choose from. Even if we just wanted to, say, measure the height of this table sitting in front of me right now, I could measure this table and express its height in meters. I could use millimeters, centimeters, and these are just units from the metric system. There are all sorts of other units outside of the metric system that we might choose to use as well, like feet or inches or yards. So a lot of units to choose from just to simply measure the height of this table that is in front of me right now. Well, scientists collaborate. We work together on projects. So it would be very, very inconvenient if one scientist was making all of their measurements of length in centimeters and the scientist that they were collaborating with was making all of their measurements in millimeters. Okay, so then they'd get together and there'd be some confusion about things and somebody would have to convert all their units into the other units, and you could see how inconvenient that could be. And that's why we have a set of units called the SI units, which are an internationally agreed upon set of units from which all other units can be derived. So anytime that your instructor says use SI units, you will hopefully know what units they're asking you to use. So let's talk about SI units next, and this is on slide 3. Okay, so I just said that there are 7 internationally agreed upon units for the SI units. We are only going to talk about 5 of them because only 5 of them are really relevant in an introductory chemistry class. And those 5 are already presented for you on slide 3. So I'm just going to copy all that information down here. All right, so starting with mass. The SI unit for mass is the kilogram. Moving on to length. The SI unit for length is the meter. So if we wanted to use SI units to measure the height of this table, we would make sure to measure the height in meters. Okay. For time, it is the second. For temperature, it is the Kelvin, abbreviated capital K, not degrees Celsius, not degree Fahrenheit. Kelvin, and we'll talk about the Kelvin scale in just a moment after we finish up SI units here. And last but not least, amount, the SI unit for the amount of a substance is the mole. It's spelled M-O-L-E, but it's abbreviated just M-O-L. So I'm going to go ahead and write that there. And I'm going to put a little star here because this won't really be covered until I get to tutorial number 8. We'll talk about moles in tutorial number 8. So for now, all I'm going to say about the mole is that it represents a number, much like a dozen represents a number. A dozen represents a number 12. A mole represents a number 6.022 times 10 to the 23rd. An ugly number, not as pretty as a number 12, but that's the number that it represents. So the mole is the SI unit for the amount of a substance, and it represents a quantity, 6.022 times 10 to the 23rd, and we will be talking about moles in tutorial 8 in much more detail. All right, so let's go ahead and erase all this. Okay, so we're on slide 4, temperature. And we just learned that the SI unit for temperature is the Kelvin, but of course more common units that we're familiar with are the degrees Celsius and degrees Fahrenheit. We're much more familiar with those two scales. Okay. So your lab thermometer will probably measure degrees Celsius. Maybe degree Fahrenheit. I've never had a lab thermometer that measured in degrees Fahrenheit. So probably in the lab, your thermometer will measure in degrees Celsius. But you will have to convert, for most of your mathematical calculations, you will have to convert into Kelvin and use those temperatures for your calculations. So you might be asking yourself at this point, well, why? We're more familiar with degrees Celsius. Our lab thermometers are going to measure in degrees Celsius. Why can't we just use the degrees Celsius scale? Why do we have to use this whole new thing called the Kelvin scale? Well, the Kelvin scale is actually a very significant scale. The temperature of a substance is related to the kinetic energy of the particles that make that substance up. So the higher the temperature of a substance, the faster those particles are moving around, the higher their kinetic energy. And the lower the temperature of the substance, the lower the kinetic energy, or the lower the motion of those particles. And at 0 Kelvin, that's a temperature also called absolute zero. And that's a temperature at which that kinetic energy, that motion, is also 0. The particles stop. Okay, so absolute zero, very important. I'm going to write that down. Absolute zero is 0 on the Kelvin scale. Okay, and so that means that there are no negative temperatures on the Kelvin scale. You have negatives in the degrees Celsius and the degree Fahrenheit scale, but not on the Kelvin scale, because 0 Kelvin is the temperature at which the kinetic energy, the motion of the particles, ceases. It stops. There is nothing colder than that. Okay, so let's go ahead and draw 3 thermometers and look at how the degrees Celsius and degrees Fahrenheit scales relate to the Kelvin scale. Let's erase a little bit of this here to give us some more room. And these 3 thermometers are drawn on slide 4 already for you, so you don't have to redraw them if you've got those notes in front of you. Okay, so we'll do Celsius first. Relate that to Kelvin, because those are the 2 that you're probably going to be converting between. We'll look at Fahrenheit, the Fahrenheit scale, briefly. Not quite as much time spent on that because you're probably not going to be dealing with it so much in your introductory chemistry class. All right, so let's measure off some important temperatures on the degrees Celsius and Fahrenheit scale. Okay, so we're going to measure, or we're going to mark off the temperature that corresponds to the boiling point of water. So I'll just write here boiling water. And the temperature that corresponds on the Celsius scale here to the freezing point of water. So I'll just write freezing water here. Okay. And then we'll do the same thing for the Kelvin scale. So water freezes at 273 on the Kelvin scale, boils at 373 on the Kelvin scale. Okay, and then we'll do the same thing over here on the Fahrenheit scale. 32 degrees Fahrenheit is the freezing point of water, and 212 is the boiling point. And again, this is all on slide 4 for you already. Okay, so let's go back to that blue pen. Okay, so comparing the degrees Celsius and the Kelvin scale first, because again, those are the 2 that you're probably really going to need to use the most. Well, the good news is that if you look at the number of increments between the freezing and the boiling point of water on the Celsius scale, you'll find that there are 100 increments, or a change of 100, all right? A change, delta means change of 100 on the Celsius scale. Same thing on the Kelvin scale. Between the freezing point and the boiling point of water, 273 and 373, there are 100 increments. So again, this corresponds to a change of 100 also on the Kelvin scale. What that means is that one increment on the Celsius scale is equal in magnitude to one increment on the Kelvin scale. Okay, now what I'm not saying, I am not saying that 1 degree Celsius equals 1 Kelvin. Clearly it doesn't. 1 degree Celsius is way up here and 1 Kelvin would be way down here. Okay, so very different temperatures. What I'm saying is that one increment on the Celsius scale is equal in magnitude to one increment on the Kelvin scale. And that's good news for when you're trying to convert between these two scales, because it means that all we have to do to convert between a temperature in degrees Celsius and a temperature in Kelvin is adjust for the 0 point, which is 273. So we're either going to add 273 or subtract 273. So let's take a look at how that's going to work. If you have a temperature in degrees Celsius and you want to convert it into a temperature expressed in Kelvin, you're going to add 273 to adjust for that 0 point difference. So the temperature in degrees Celsius plus 273, that's going to give you the temperature expressed in Kelvin. Let's go the other way. If you have a temperature in Kelvin and you want to express that temperature in degrees Celsius, you're going to need to subtract the 273 to adjust for that difference in the 0 point, and you will then have your temperature in degrees Celsius. I'm going to circle these two equations because you most likely will need to be able to do this from memory in your introductory chemistry class. Go between Kelvin and Celsius. Okay, so add or subtract the 273. Now, one quick note before we go on. It's really 273.15 and 373.15, but every introductory textbook that I have come across always drops the 0.15 for an introductory chemistry student, so I've chosen to do that here as well. So pay attention to your own instructor, and if they want you to use the 0.15, make sure that you do use the 0.15. Okay, so just really quickly, let's look at the Fahrenheit scale. We won't go into too great of detail here, but the first thing I do want to point out is that the change between the freezing point and the boiling point of water on the Fahrenheit scale is not a change of 100. It is a change of 180. Okay, so that means that one increment on the Fahrenheit scale is not equal in magnitude to one increment on either the Celsius or the Kelvin scale. In fact, for every one increment on the Celsius scale, you would have 1.8 on the Fahrenheit scale. Same thing for the Kelvin scale. For every one increment on the Kelvin scale, it will correspond to a change of 1.8 on the Fahrenheit scale. So when you're converting between the Fahrenheit scale and one of these other scales, you not only have to adjust for the 0 point difference, you also have to adjust for the fact that one increment on the Fahrenheit scale is 1.8 times greater than an increment on the Celsius or Kelvin scale. So you have to multiply or divide by the 1.8, and you have to add or subtract for adjusting that 0 point difference. So again, you probably won't be dealing with this scale in an introductory chemistry class, so we won't look at that calculation, but that's why it is a more complicated calculation. Okay, so let's go on now to slide 5. Okay, volume. Refers to the amount of space occupied by a body. The SI units for volume are derived from length times width times height. So I'm going to write here SI derived units based on length times width times height. So meters times meters times meters, and we get the meter cubed. However, much more common units are going to be milliliters. It's probably what you'll be measuring mostly in the lab. Maybe liters, and also probably centimeters cubed. For like a regular shaped solid, you'll use centimeters cubed. Okay, so I like to do a little visual for volume and show you how the units of liters and milliliters relate to meters cubed and centimeters cubed. Okay, so let's take a cube with a length of 1 meter, a width of 1 meter, and a height of 1 meter. So this is supposed to represent, let's go to a different color here, 1 meter, 1 meter, and 1 meter. Okay, so my drawing's not very good because this should be a little longer, but hopefully you won't hold that against me. Okay, so 1 meter cubed. Well, if we carefully measured off 1/10 of the length, 1/10 of the width, and 1/10 of the height, and pulled that smaller cube out. Okay. So now we've got a cube that is 1/10 of a meter in length, 1/10 of a meter in width, and 1/10 of a meter in height. We'll go back to the metric system. 1/10 of a meter, that's a decimeter. So this new cube here is 1 decimeter in length, 1 decimeter in width, and 1 decimeter in height. Or in other words, it is 1 decimeter cubed. 1 decimeter cubed is the same thing as 1 liter. 1 decimeter cubed, let's write it here, equals 1 liter. And I think that that's a good conversion to know. Okay. Now, if we carefully, once again, measured off, and let's do this in blue this time, 1/10 of the length, width, and height of that decimeter cubed, and pulled that smaller cube out once again. My drawing is not that beautiful, but hopefully you see that this is supposed to be that little cube that we pulled out there. So that would have 1/10 of a decimeter for its length, 1/10 of a decimeter for the width, and 1/10 of a decimeter for the height. Well, again, go back to your metric system. 1/10 of a decimeter is a centimeter. So that cube would be 1 centimeter in length, 1 centimeter in width, and 1 centimeter in height. Or 1 centimeter cubed, because 1 times 1 times 1. 1 centimeter cubed. Well, 1 centimeter cubed is the same volume as 1 cc. cc just stands for cubic centimeters. cc's are used a lot in the medical field, so I think that's a good thing to know. So let's write here, 1 centimeter cubed is the same thing as 1 cc, and that's also equal to 1 milliliter. Again, a good conversion to know. Okay, so if you have a problem, you're trying to work a problem where you're converting between centimeters cubed and milliliters, well, they're the same thing. Okay, so that's good to know. All right, slide 6, density. Density is a measure of the amount of mass per unit volume of a substance. So I'm going to write here mass per volume. Or D equals M over V, where D stands for density, M stands for mass, V stands for volume. This is an important equation to know in an introductory chemistry class, so I'm going to circle it. Okay, so that means that our SI units are derived, SI derived units. Mass, we know has the SI unit of the kilogram. Volume, we just saw, had the SI derived units of meters cubed. But much more common units that you'll probably see in the lab would be grams per milliliter, grams per centimeter cubed, which of course we know centimeters cubed and milliliters, they're the same, okay? Same volume, and grams per liter as well. So those will be more common units that you'll see in reference books, your textbook, and probably what you'll measure in your introductory chemistry lab. Okay, so to just kind of solidify this concept of density, let's go ahead and look at an example. And for the example, I have chosen two very common elements, things that I'm hopeful that you'll be familiar with already. Okay, so I have looked up the density for the element lead. And let's compare it to the density for aluminum. You're already probably thinking something very dense versus something very low density. Okay, so again, I looked up these densities already. You don't have to memorize these. You would just look them up as needed. The density of lead is 11.3 grams per centimeters cubed. The density for aluminum is 2.7 grams per centimeters cubed. Okay, so if we had a 1 cubic centimeter sample of each of these substances, 1 cubic centimeter sample, so the same volume. Let me try to draw that here. A 1 cubic centimeter sample of lead. This represents 1 cubic centimeter of lead. And I'm going to try to draw the same volume over here. You already know I'm not the best at drawing, so this is supposed to be the same volume. This is supposed to represent 1 centimeter cubed of aluminum. So the same volume, but imagine you had the lead over here in your right hand and you're comparing it to the sample of aluminum in your left hand. Again, they have the same volume. They're both 1 cubic centimeter, 1 centimeter cubed. Okay, but because the lead is roughly 4 times more dense, okay, clearly that sample is going to have about 4 times the mass, much more mass per unit volume, about 4 times the mass per unit volume for the sample of lead. The aluminum, much less mass per unit volume because it's a much lower density element. It's going to feel much lighter. It's going to have a much lower mass. So what is the mass going to be? I purposely chose 1 cubic centimeter so we could easily say the mass of this sample, let's write it in blue, of lead is going to be 11.3 grams. We just know that because we already have the density written up here. For every 1 cubic centimeter, there's going to be 11.3 grams of mass. But over here for our aluminum sample, which is much less dense, this sample is only going to have a mass of 2.7 grams. So this is a 2.7 gram mass sample of aluminum. Okay, so this will conclude our tutorial number 1. I hope you will consider tuning into problem set 1, which just has a bunch of problems that we will work together based on the concepts that we just covered here in tutorial number 1. Thank you very much.